The subject of this session is going to be the recent research involving the proposal that there was an extraterrestrial impact that took place on planet Earth, specifically somewhere in North America in, I guess, northeastern part of North America, and the timing of the proposed impact coincides at about 12,900 years ago. So it would come just at the end of the last ice age. And stratigraphically, the proposal is that this impact is associated with something that archaeologists have known for a long time as the black mat. It's a very, very widespread geological marker bed that extends from Catalina Island into Maine, and the claim is made now that extends as far east as Germany. And so we have this session today as a follow-on to a presentation that was given last night on the campus of NAU, and we've assembled a panel today to discuss and debate some of the technical aspects of that from the astronomy and geology and geochemistry sides of things. And we have a very distinguished panel of presenters today, and I'll start from left to right. At the end of the table here is Mark Boslough from Sandia Laboratories. He is an expert in computer simulation of airbursts and extraterrestrial impacts of that sort. He has an article in National Geographic, this month's issue of National Geographic, on his work. We have seated to his right Carolyn Shoemaker, astrogeologist extraordinaire and associated, I'm sure, as you all know, with the Shoemaker-Levy comet from a few years ago. We're very honored to have her here today. On my left is John McHone, who is from the Arizona State University Planetary Geology Group. On my right is Alan West, one of the researchers who was involved in the original proposal of the comet impact, and at the end of the table is Ted Bunch. Both are from NAU and both are co-authors of the PNAS article that presented this research, I believe it was in October of last year, September, October of last year. One of the things I wanted to do before we got started was to provide a little bit of context for this research from an archaeological point of view, and I wanted to start by talking about where we have come since 1927. The general theme of this year's meeting here in Flagstaff, I guess if we had to put it in terms that would have been recognizable in the very first Pecos conference, would be that we're discussing now in some considerable more detail what was known then as Basket Maker 1. And in 1927, Basket Maker 1 was a very nebulous, mysterious, not very well understood period of time of unknown duration that represented that time before people grew corn and made pots and lived in pueblos and left the very visible archaeological remains that we all know very well. One of the things that is very striking about what's happened since 1927, and every now and then I just have to sort of remind myself of what it is that human beings are capable of doing in their curiosity and studies of the world, we now have an extraordinary understanding of Basket Maker 1, to put it in those terms. We've come a long way, baby, since 1927, and the kind of the culmination of that understanding, at least at the very earliest end of things, is a paper that was published just this May by C. Vance Haynes of the University of Arizona, who I'm sure you all know is the preeminent researcher on the Clovis culture and the time period that we're talking about. In fact, I think no one on this earth has seen more black mat samples and more alluvial stratigraphy from that period of time than Vance Haynes. He couldn't be here today. I invited him to be on the panel, and he gave me the best excuse that anyone can ever have, that he's going to be home writing the results of his life's work. And Vance just celebrated his 80th birthday this year, and I'm not going to be the person who interferes with Vance Haynes writing up his life's work. So we're happy that he's not here, in a way, that he's home writing. What I want to do is call your attention to the fact that since 1927, we've learned a lot of things that, as one person has put it, all of us who work in the historical sciences, and that being archaeology, paleontology, astronomy, those historical sciences routinely discover things that we have no right to expect to know. These are things that are extraordinary, that we even know about these things. And what I want to point out, and I'll quote briefly from Vance's article from May, is that I think we're on the threshold of achieving a very important consensus and set of empirical generalizations about what happened at the end of the last ice age. This article that Vance published in the PNAS really lays out the extraordinary nature of the black mat and what it is that distinguishes it in archaeology. It has a clarity and a certainty that is almost unknown in archaeology. And I would like to start by quoting from that article, the very last paragraph, in which this, in a way, sets the table for what we're going to talk about today. And whether or not there was an extraterrestrial impact of the nature that's been proposed, whether or not there was an extraterrestrial impact at all in some people's view, what is the scientific evidence for that? How do we debate that scientifically? How do we know the truth or the non-truth of some of the proposals that are being made? That's the fun part of science, and that's what I hope we get a little closer to today in this discussion. But I'd like to start by quoting from Vance Haynes's article, the very last paragraph of that article that really makes a summary that is as plain as it can be. And the very last sentence of this article summary is, "I reiterate, something major happened at 12,900 years ago that we have yet to understand." And what he's talking about, when Vance Haynes says something major, Vance Haynes is not a man given to extreme statements, and there's not going to be a statement in print in a journal of this nature unless he believes that to be the case without a doubt. And so I want to back up a little bit then and talk about what it is that he's talking about. What is the extraordinary event that Vance Haynes refers to in this article? The black mat is a widespread stratigraphic marker that is notable for its abruptness. There is a set of empirical generalizations, summaries of what the facts are on the ground, that are pretty extraordinary. The fact is, most of the Pleistocene megafauna, in fact all of the Pleistocene megafauna except the bison, did not make it through to the times after the black mat. And the end of the Pleistocene megafauna is with the black mat. At the time just prior to the deposition of that layer across the continent, and it by the way, is not always black. It ranges in color from truly black to actually very light gray or white in color. It seems to vary from place to place in terms of what it is, what formed it. In some places it's an algal mat, in other places it's a sediment deposit of a different kind. So it's not always black, and it's not always formed under the same conditions, but it is always associated with the date, radiocarbon calibrated date of about 12,900 years ago. There is no pre-Clovis or no projectile point style that we know predates Clovis ever found under the black mat. There are no megafauna besides bison found above the black mat, and there are no Clovis remains ever found in the black mat. Those are the three summary statements that are made. This article, by the way, I believe would represent the life's work of Vance Haynes in terms of what he's done. He in this paper discusses 97 sites, Pleistocene, terminal Pleistocene sites. He finds that of those 97 sites, 70 of them have faunal remains. Of those 70 sites, 70% of them that have faunal remains are in direct contact with the black mat. And in some cases, the black mat is found draped over the bones of the animals. And one of the most notable cases of this is Murray Springs, where if you're familiar with what was done at Murray Springs, they discovered a mammoth that had been killed at that place and partially butchered. The mammoth was nicknamed Eloise the elephant. And so when you hear Eloise, then we're talking about that particular specimen. The black mat was draped over the bones and actually stained that elephant. The site of Murray Springs had elephant footprints in the mud that presumably were from that very elephant. I believe, as Alan tells me, the footprints led to the mammoth carcass. pretty good evidence of that being the case. Those footprints were preserved, and the way they were preserved apparently was sometime at the time the elephant died, immediately after that, the water table began to rise, and it rose to the point where the mud was preserved, and the elephant carcass was preserved, and it was covered by the black mat deposit. I think I've probably said just about all I need to say about that. And just to summarize, we have a geological deposit, a marker bed that is spread across the North American continent, and evidently, and we'll hear a little bit more about that, I think, into Europe. It is the case that it has a relatively precise radiocarbon date range of about 12,900 years for its initiation. It never has Clovis remains in it. It never has megafauna above it, and it's just an extraordinary finding in archaeology to have that kind of clarity and that kind of definitive stratigraphic evidence. The words that Vance Haynes uses are abrupt. He runs through in this article, one last thing, he runs through in this article that he thinks the extinction and the event that terminates the Pleistocene is, in his words, synchronous and instantaneous. And the various things that have been proposed to explain that in the past include the overkill hypothesis, most famously associated with Paul Martin. Vance Haynes runs through the possibilities of overkill, and his quote here is that Martin's overkill hypothesis posits humans as the sole cause, but could they do it everywhere in the same instant? That's his rhetorical question regarding overkill. And the notable word here is instant. He's proposing that the megafauna and the end of the Pleistocene came in an instant. He runs through the possibility of climate change being the cause for the extinctions. But he doesn't think enough time elapsed, so he says, Lundelius and Graham invoke climate change, but this, like overkill, would seem to require more time than the evidence for stratigraphic abruptness allows. Stratigraphically abrupt. Pleistocene comes to an end in an instant. I find the language in here to be pretty remarkable in terms of what is being said about the nature now of what we think we know about the very beginnings of Basket Maker 1. And I want to also conclude here by, finally conclude. I promised that several times now, but I'm finally going to conclude. In this article he says, therefore, this is just the beginning of scientific study to see if an ET event can be verified to explain the Rancho La Brea termination. And so that's what we're here today to talk about, and that is whether or not an ET event can be verified. And I say let the debate begin. And what I'm going to do now is, I think, start with the panel from right to left. I want to give Ted and Alan a chance to summarize, for those of you who might not have been able to attend the presentation last night. I want to give them a chance to summarize what they found, and then I want to move down the table in order and have statements about the skepticism and the questions that remain about what they've proposed. So, would you like to start, Alan? Okay.
I want to continue with a little bit about Eloise, because Eloise is a good starting point for what we found. Some of the best markers and evidence for what we think is an ET impact came from very close to Eloise the mammoth. And one of the curious things about that is the footprints at Murray Springs do lead up to where Eloise was found, and the black mat was actually pried from these footprints. There is no other stratum between the footprints and the mat. For those of you that weren't there last night, Vance Haynes asked an African elephant expert to take a look at the skeleton, and he concluded that because of the way the skeleton was articulated, that the animal cannot have been dead more than 2 weeks before the black mat formed on top of it. So very likely Eloise was one of the last mammoths alive anywhere on the continent. And the curious thing about it is that at Murray Springs we find 14 different markers that we think suggest this ET impact. That, of course, is the debatable part. What's not debatable is that Eloise and all the mammoths disappeared. But at Murray Springs, in the footprint and on top of bones, Eloise is gone, but there were other mammoths at Murray Springs. The top is stained black by the mat, and the bottom, which was still in the Clovis sand, is unstained. When I tested those, the top of the bones are mildly radioactive and magnetic, and the bottom half is neither. And we find these markers absolutely draped over these bones. We find them right at the bottom of the black mat and this very thin millimeter layer between the level that the Clovis people were walking on, and including Eloise, and the black mat. So we have what's actually a beautiful datum for that time. And for those of you or anyone that's working in the Clovis horizon, with a $30 magnet and a bucket of water, you can find 2 of the 14 markers that we find there, and we found them at virtually every one of the 30 sites we've looked at, from offshore California and the Channel Islands all the way to Topper in South Carolina and on into Belgium and Germany. And where the black mat exists, not at every site, but where it does exist, we find these markers right at the bottom of it. So anyone with a magnet can go to a wall, find these peak and magnetic grains that have these little melted iron balls in them, magnetic spherules. And so within a few minutes, if you have any doubt about the age of a site as an archaeologist with a $30 magnet, chances are you can answer your question. Whether or not there's a map there, which is an obvious visual marker. So we'll be the first to admit that we don't know what happened. What we find are these enigmatic markers, one of which is diamonds. We find these tiny diamonds that are about the size of a coal virus. Some of them just recently we found are 0.5 millimeter. That's the biggest we found. We're finding those all across parts of 2 continents, and we find them only in this layer. They're not below it, we've looked. They're not above it, we've looked. They're only there. So while we don't know exactly what happened, like Van says, we know that something extraordinary happened. And the best explanation that we've come up with is an ET event. Though frankly, we don't know what that was. We think it may have been a fragmented comet, but since no one's ever seen anything like that before, it's pretty hard to come up with any definitive proof. But all the markers that we have point to an ET event, but what we do know is that the animals, tens of millions of animals, went extinct right at that geologic instant. As he said, not a one of them has ever been found in the mat or above it. And this is tens of millions of animals: mammoths, mastodons, saber-toothed tigers, giant sloths, short-faced bear, peccaries, giant beavers. All of those animals, which were even in some of these woods around here 13,000 years ago, they're not here now. And so that's the real mystery. Where did they go and why? And that layer tells us that that was the end of them. And curiously, Clovis went through a major transition too. There are no Clovis points above them. The technology to make Folsom points and redstones and all the successor points is a different technology. And so anyone who looks at those points and knows how to make them says, yes, this is Clovis, that's Folsom, and they're not the same. So that's where we stand now. There's a lot we don't know, but there's a lot that we do know. And the hardest to explain is, where did these diamonds come from? The one type of diamond that we found is called Lonsdaleite. It's a hexagonal diamond. It's only known to occur in 2 places on this planet. It's either found in meteorites that fall, or it's found in meteorite craters caused by the impact itself. And we've now found Lonsdaleite at 3 sites from offshore California into Germany. So the real mystery is, how did those diamonds get there? It takes extreme temperature, extreme pressure to make them, and none of those conditions are known to exist at the surface of the Earth. So that's where we stand today. And Ted is more of our impact expert. So he was chief of exobiology at NASA for a fair amount of his career, latter part of his career. He's now retired at NAU. So I'm going to pass the baton to Ted.
Thank you. Good morning, everyone. May I see a show of hands for those who did not attend last night's presentation? You're excused. It makes my job simpler to summarize what happened last night. My goodness. Well, as Alan said, we have these wonderful markers, and Vance Haynes and other climatologists, glaciologists, everyone has pointed to the fact fact that 12.9 thousand years ago, something extraordinary happened, and it happened almost instantaneously, affecting cultures, the extinction of animals, changing of circulation patterns in the ocean, a huge cooling event, a lot of things which could not necessarily be caused by a slow sort of event. It has to be more of a rapid event, almost instantaneous, as has been said. So what we have to look at, we have all this information, and we have to put it together to come up with something that's respectable as some sort of a vehicle. And the people here to the left are adversaries because they don't like any of this. No. In science, you have to argue back and forth, and that's the process of scientific thinking and thought. I might remind you that until 1961, no one believed there was such a thing as a meteorite crater. And Carolyn Shoemaker's husband, Gene Shoemaker, and along with Ed Chow and a few other people, were the first to prove that Meteor Crater, Arizona, was actually an impact crater. Since then, and that's only been, some less than 50 years, we've now found 180 impact craters throughout the world, some 2 billion years old, some as recent as Caracas in Peru, which is a very small crater that happened a couple of months ago. So this happens all the time, and due to erosion and weathering and burial, a lot of the crater remnants we don't see. However, with respect to our Younger Dryas event, we don't expect a crater. We don't see one because that was only 13,000 years ago. We'd expect to see something, we don't. And we think something happened over the Laurentide ice sheet that covered most of Canada at that time, causing the rapid breakup of that ice sheet. Huge amounts of meltwater emanating out into the Atlantic, changing the flow, the cooling, heating engine in the North Atlantic from southern latitudes. So we had to come up with some answer. Now, in 1980, the Alvarez team from Berkeley has said, okay, a comet hit somewhere in the Earth, causing the extinction of the dinosaurs. They had pretty good lines of evidence, but they didn't have a crater. It took 8 years until a crater was finally found in the Yucatan Peninsula called Chicxulub. And at the time, 65 million years ago when this happened, that was mostly a shallow sea. And most of it is still underwater. Some is buried in the jungles of Yucatan. Anyhow, make a long story short, there was evidence finally found for a crater. We don't propose an impact to make a crater. What we propose is something called aerial bursts that Mark has done a lot of computer simulation studies on, some of which he can speak to and some which he can't because he comes from a secret laboratory. So we have an impasse here. He can only say so many things, and we can only say so many things because we have a paper or two that either has been submitted or will be submitted, and the information therein is proprietary. Therefore, we have a 50% It's like playing half a ball game, and we're tied. So, but at any point, I think we can work with the evidence at hand, and our colleagues to the left-hand side of the table can give their opinions about our particular vehicle, which is an aerial burst that struck the ground, probably over the Laurentide ice sheet, maybe some on the periphery, because in addition to the diamonds that we find from Channel Islands to Belgium, to Canada, to the Carolinas, we have carbon spherules, melt spherules, we have glassy carbon, we have other indicators of very intense short-term melting, quenching of material. You don't get that from ablation because if these diamonds had come in from ET sources, they would not have survived the ablation effects. Diamonds do not like temperature once they're formed. The shock diamonds, of course, the hexagonal Lonsdaleite, are pretty good indicators of shock. They can only be made by shock. Whether or not they formed in outer space and survived, or they were formed here, is part of our project. That's work in progress. What Alan didn't mention here, but mentioned last night, is there's a third form of diamond. It's called N diamond, meaning new diamond, and it's a diamond not formed by high temperature necessarily, or high pressure. It can be formed in a variety of laboratory, industrial processes, and we find those by the truckload at the YD boundary. These are formed by a unique set of temperature pressure circumstances, not outlandish, but they survive because of the quenching effect. They have to quench from a certain temperature and pressure within a nanosecond. So it just can't go out and make them in a bonfire. You can't make them in forest fires. We have looked at the glassy carbon spherules in present day firestorm areas, and there are no diamonds. We've looked at what, 7? And we keep looking. We keep looking to see, just how far we can go with saying they don't form in modern fires. Now, these could have formed in an impact, an aerial burst that involved both the impactor and touching the ground with the materials from the ground. This is what we really have to study. The fact that an event happened, we have good evidence that it was a very vigorous, short-term, dramatic event which changed the course of lives and history of North America and probably part of Northern Europe. So right now we are stuck with exactly how this happened, and I will turn this over to our colleagues to the left, and maybe if they don't like our ideas, maybe they have an answer.
Okay, my name's Mark Boslough. I'm from Sandia Labs. I should tell you what my background is so you can dismiss what I say when I start talking about things I know nothing about. I'm a physicist. I did my PhD work in geophysics, so I'm conversant in geology, but then when I start getting into paleontology, archaeology, things like that, I'm completely speculating. And we were described as adversaries, but we're friendly adversaries.
Science always friendly.
So far. So when I first heard about this, I guess it was about the time of the American Geophysical Union in Acapulco. That was May of 2007. And the first thing I thought was, this is crazy. And the main reason is I'm a follower of Carl Sagan. I read a lot of his books, and he was a very skeptical scientist. And he had a phrase that he used to say, extraordinary claims require extraordinary evidence. And there's no doubt that something very extraordinary happened at 12,900 years ago. No doubt whatsoever. A very abrupt climate change. But other time, and stratigraphically very abrupt. But that's not the only time in history that we've had very abrupt climate change that has nothing to do with impact. In fact, there was a paper that came out in Science just last week, and it was written by a group at Copenhagen. The lead author was Stephenson, and they were looking at Greenland ice cores. There's a new ice core being drilled at the Northern Greenland Ice Core project. And they have a new technique where they're actually able to do this continuous flow analysis. And they can actually get sub-seasonal resolution, not just sub-annual, but sub-seasonal resolution. And at 14.7 thousand years ago, there was a climate change that was even more abrupt than the one at 12.9. In central Greenland, they have proxies for temperature, they have proxies for many things. But the oxygen isotope ratio in the ice at that time changed radically and indicated a 10 degree Celsius temperature change over central Greenland, and that's about almost 20 degrees Fahrenheit in less than 3 years. And that was accompanied by a complete rearrangement of global circulation, and that the proxy for that is dust. They actually see dust in the ice, and the dust is blown off deserts in Central Asia, and the dust increased. There are other isotope ratios that change, indicating where the snow is coming from, and that shifted very abruptly as well. And so they also looked at the Younger Dryas, and clearly that's very abrupt as well. And then there's a third one, and that's actually when the Younger Dryas ended, and that also changed very abruptly. And so, you know, we've got 3 events in a period of several thousand years that were just as abrupt stratigraphically, and no evidence for impact. Now, in terms of evidence for impact, there are a lot of interesting things that are found in this black mat, none of which are considered diagnostic of impact, unambiguously diagnostic. They can be indicators, but there are, you know, the diagnostic indicators of impact are shocked quartz, high pressure phases of silica, the ones that John Shoemaker found in Meteor Crater, Coesite, and Stishovite. Those are not found, and the size of and my original reason for being very skeptical is the size that's claimed for the asteroid or comet, 2, 3, 4 kilometers in diameter. If you look at the frequency of impacts of that size, they happen on the order of once every 10 million years. And we're talking about something that happened 10,000 years ago. So the likelihood that something like that happened very recently is very low. So it's an extremely low probability event that this could have happened that recently. And I think the implausibility of that scenario is my main reason for skepticism. And I will pass the microphone to Carolyn.
Hi, I'm Carolyn Shoemaker. I'm basically a planetary astronomer. I specialize in finding comets. I don't know a lot about your line of work, but I've been trying to read about it in the last couple of weeks. I first heard about black mats perhaps 3 years ago, 4 years ago, and dismissed the idea out of hand as not being realistic. And the problem for me is this. We hear an awful lot about impact. Impact has become fashionable. The idea that something would hit the Earth and cause a crater is a very exciting idea. And consequently, people are looking at maps, they look at the area around them, and they see round things like craters, and people think in terms of craters, but they don't often think in terms of airbursts. So I did a little investigation on Tunguska to see what really happened there, what we know about it. And Mark was there not very long ago for the anniversary, he said he did not see many trees that were down, but that's what we associate with Tunguska when we see the pictures. Tunguska was a very interesting event. We know what happened, but exactly how large the body was that caused it, we don't necessarily know. It might have been about 50 meters. If it were a very big object, it would have made a crater, and we don't have a crater. What we have is the effects of an airburst, a blast effect. But we don't have the ordinary things that I look for when I say and impact. And impact has various features that we associate, perhaps, with the KT boundary. Diagnostic things that these gentlemen have dismissed out of hand because we don't see them in association with this particular event, the Clovis extinction, the black mass. So I can't look for those particular diagnostic features here. I have to find others. And as I look at the markers that they present, I am not convinced that any of them are totally diagnostic, that you find all of them in association with the climate change and with the extinction. This was not what we would call a mass extinction because it mostly took out the megafauna, the big animals, but not necessarily the people, as was presented last night. People moved on. Sea life was not affected very much by this, if at all. It was a land event. So I asked myself, can a comet do this? Usually we think of comets, as small comets, as breaking up in our atmosphere. They ablate very quickly. If this were a large comet, it seems to me that it would go through the atmosphere and possibly through the ice. I don't know why ice should be any different than rock. Perhaps it is. From an impact, in which case we should have a crater. I can imagine that it would certainly affect the ice sheet. But if a comet comes in at approximately 60 kilometers per second, it comes through the atmosphere if it's a large one, and it will come through the ice. So I have trouble envisioning this as an airburst. Large comets, for the most part, have not come close to the Earth in our history. Doesn't mean that they haven't come through. Possibly some of the largest craters on Earth were caused by a comet, because a comet comes in at such speed. I have trouble with the diamonds. I don't quite know where they came from. I have trouble with the carbon spherules. There are a number of these markers that I think we could find in an ordinary situation without resorting to impact. I think at this point I'll turn it over to John, and he can see what he comes up with.
Thank you. My name is John McHone, and I've been working on meteorite impact craters, terrestrial craters, for quite a long time. I first started in 1973 when I was invited by Robert Dietz to go to Colombia, South America, and look at a suspected impact crater called Tequendama, or La Laguna de Tequendama. I was just wrapping up my master's degree in oceanography, nearshore processes, and I walked by this doorway at the laboratory in Miami, Florida, and this gray-haired guy was sitting in front of a very clean desk with two pieces of paper. This was Robert Dietz, and he points to me and says, "You, do you want to go to South America?" And I said, "When?" "Tomorrow." And I had just handed my thesis to my advisor to review, and I said, "I'll have to go ask him, but I'll be back in an hour." So I went over to ask Don Swift, and he says, "Get out of here." He didn't want to read my thesis that week. and 48 hours later, I'm in Bogota with Bob Dietz, and we're looking at this solution pit, or this round hole in the Andes Mountains outside of an old quaint little colonial town called Tequendama. And it took us about a half a day of walking around this thing to dismiss it as an impact. It did not have the characteristics in Bob's mind of what you would expect. This is my first experience with a meteorite impact crater. A couple of years earlier, I had been in Vietnam. I had the pleasure of being drafted and sent, and I saw lots of craters, so I knew pretty much what small craters look like. In fact, I made a lot of them. And one of the local questions there in Colombia, in the Andes, was, how deep is this thing? And nobody seemed to know. Well, we don't know. And it wasn't a very big crater. It was only about 400 meters across. So Bob says, peel down. Here, take this rock and this string. So we swam out to the middle of that crater and lowered the string, and it was only about 15 meters deep. And we came back. Just on a little side note here, early this year, I got a letter from a researcher who is compiling mountain lakes all over the place, and he wanted a copy of our bathymetric map and how we conducted the survey. So it took me just a couple of minutes on the telephone to fix his chart. At any rate, I've been working on impact craters ever since. Bob was a pioneer in this particular field, and I've grown to learn a lot about impact craters on Earth. And what we're dealing with in today's topic is quite different from my real experience. I work with a hard target, something that has suffered ferocious impact and the equivalent of an explosion. In order to understand what these things are, you'd better have a little bit of a background in other holes in the ground, what karst sinkholes look like, what volcanic craters look like, what the projectiles that come in from space look like, and what you can expect to be there. Now, when a cometary shower was first brought to my attention concerning this particular topic, I saw the published abstracts from the Acapulco AGU meeting. And my first thought was, these guys are wacko. What are they talking about? They were proposing almost, it was as if they were grasping for straws to support an impact of any kind. They were throwing out the Carolina bays, the thousands of little round lakes along the eastern seaboard. They were talking about magnetic spherules. They were talking about mammoth bones with impacted iron fragments in them, and said, well, I'd better take another look at this. I dismissed it at first, but then I'd better take another look at it. And as more and more formal publications come out, there's a lot of information in here that I don't quite understand. I don't follow just where the nanodiamonds are coming from. I do know that my Australian colleagues who work with diamond exploration tell me that microdiamonds are so common that they're useless as a prospecting tool. You can't use them to track back. Well, this doesn't really negate Ted's story about these things being widely spread, but what are we talking about? How big are these things? The size of a cold virus? Who's qualified to find them? How do you separate them from your sample? There are a lot of questions that are going to deserve a closer, longer look. Quartz is the most common and most abundant mineral on our Earth's crust, and it's a tough one. Once quartz is formed, it's very difficult to get rid of it, and that's why it's so well studied, and that's why it has been detected as a tool for shock metamorphism. When a high-speed projectile comes from outer space, smacks into a sandstone, a lot of that quartz can be damaged in ways that are identifiable by a skilled operator, and according to the public press, by almost anybody, as having suffered a shock event. You develop little optical planes inside the quartz grains. Well, here at the Pleistocene, end of the Pleistocene event, There are no quartz fragments, and to look for that happening, how do you do that? Well, you do away with the crater. You don't have a sandstone target. You have to impact someplace else, and ice certainly gets rid of it. If you were to make a big crater in a continental glacier, and the glacier melts, where did the evidence go? It has to come only from the projectile itself. And there I'm not really that well versed. I don't know what comets are made of. And in fact, every time a spacecraft comes back with new data, they're made of something else. It's not quite a garbage can, but if you want something strange, you can put it in a comet body and then do away with it by blowing the thing up. I've worked on very similar projects, and even with Ted down here at the end, and we don't always agree, but we're friendly antagonists, and many times we do agree. My experience with anthropologists and archaeologists, almost all of it comes from my graduate work at University of Illinois, where the geology people, especially the field geology people, the anthropologists and the archaeologists, hung out in the same bars. I learned to really get along with the archaeologists. They would sit down and drink lots of beer. And I learned to get along pretty well with the anthropologists, but the South American guys kept coming back with their own drugs, and that was a little risky, and I stayed away from the chemists. They made their own, and that was really, really bad. But this was my field of exposure to anthropology, and we cross-fertilized a lot of good ideas. There were many projects that went into the field. They were aware of what impact craters looked like, were aware of what volcanoes looked like. It was really rewarding. I'm kind of happy to be here in front of this bunch. I noticed in your early program that beer is considered a gift item. And I said, yeah, okay, those are the ones I remember. But I'm not sold on all of what they're calling the ET markers. Iron spherules are awfully common in modern sediments. They're a product of industrial processes. Smokestacks are loaded with them. It's not just iron, it's an iron nickel content that defines what a meteorite is. If you have a lot of iron around, did it come from a meteorite or did it come from a comet? The material or the information we right now have of comets is that they have very little iron in them. Meteorites have iron in them. So what is it you're dealing with here? A good solid meteorite? No. How did you get that iron? I don't really know. The volume of the nanodiamonds, I'm not comfortable with that yet. I did attend last night's talk, and just as a educational aid, they tossed out a slide that showed this sphere the size of Manhattan sitting over Manhattan, and said if you took all of the nanodiamonds and put them back together, this is the size that you would get. Well, what we know about interplanetary dust particles and some information on comet-captured particles is that, yes, nanodiamonds do exist, but they're sprinkled very, very sparsely through the host material. Now, if we glue all of the target material, if we glue all of these nanodiamonds back together, and we get a sphere the size of Manhattan, well, how big did that parent body have to be? This is getting awfully large, and that's when you start entering, the item itself, the projectile itself is larger in diameter than our atmosphere. How did it break up? Was it gravity that broke it up? Did it break up by the atmosphere? What happened here? It's a field for a lot of future research. The other markers and the other stories, when I went back and looked at the earlier literature, there is a blizzard of popular literature, of reporters putting what some people think are facts, and it's actually the product of a deadline and a telephone conversation and maybe a couple of beers. But it's really hard to sort out the popular literature of what the hard science looks like. Who processed these samples? How did they get the nanodiamonds out? Not just anybody can do that. It takes a pretty skilled operator to find these things and to identify them. And Ted down there is volunteering to, or confessing. And I haven't had a really good chance to sit down with him and see just how all of this stuff was done. I've sort of, I won't say vented my spleen here, but my experiences in verifying terrestrial impact craters in hard rock, so I'm in a little soft territory for me. And I think we'll pass this on and see if we can't start some good fights.
That's our hope, and that's why I'm sitting here in the middle between these two. I may need some help, so I think I'll just pass the discussion back over here and see if we can get some replies to what's just been said.
Yeah, first thing, I'm really puzzled. Obviously, they mention regular impacts, and all three of them say they're very familiar with hard impacts. And when a big object slams into the earth, it produces shocked quartz, melted rock, lots of things, the proxies that we know, including a crater. They are faulting us for not having the three of those, and yet all three of them will admit that Tunguska is an ET event, is an impact. There is no crater, no shock quartz at Tunguska, there's no melt products at all. So on the one hand, they fault us for not having a crater and all of those things when they admit that Tunguska is an impact. So that seems kind of odd to me. What we're talking about is a non-traditional kind of event. Tunguska was a non-traditional impact, left no crater, no shock quartz, but yet it did produce magnetic spherules. They're all over the place. They did find some iridium, they did claim to find diamonds, and yet it never hit the ground. In fact, Mark has modeled exactly what happened at Tunguska, so he well knows there is no crater, there is no shock quartz, and all of these other things, so that's a real puzzle to me. The other thing he says, curiously enough, is that because this happened 10,000 years ago, it could not be an event which would take 10 million. But I don't know if any of you have been to Las Vegas? Good laughter, huh? Well, you know that your chances of drawing 4 aces out of a single deck are the same every time that deck comes up. If you take any 10 million year span, the odds of having an impact on a given day are exactly the same every day for that 10 million years. So the fact that 10,000 years have passed means nothing. What if the last impact was 50,000 years ago, 65,000? Then it's actually fewer impacts than there should be. So you can't argue this statistically, because you can have one impact one day after the other and still have it be statistically accurate. So you can't say just because it's 10,000 it's too young. But the main thing, I think, is that most of this argument happens about what was this thing. This was not a classical impact. It did not hit the ground. At least we haven't found the crater. We haven't found shocked rocks. But for those of you that there were last night, we lined up 14 different markers. The YD event has more markers that match the KT, magnetic spherules, iridium, fullerenes, diamonds. They're found in the KT too, and they're also not found above the KT or below it, and they're the same nanodiamonds that we found, exactly. And this was used, and to answer one of the questions, this was found using classical, the gold standard of detecting diamonds. The samples were put through 150 steps of acid dissolution, various acids one after another, to get rid of everything that was not diamond. They were looked at with a TEM, which produces diffraction patterns, which is as unique as your fingerprint. Each one of you has a different fingerprint. Diamond has a different fingerprint than quartz. There's just no mistaking what it is. We've looked for these nanodiamonds above the YDB layer and below it, and they're not there, so there is no background for these things. They just don't exist at these sites, and we have looked. And they exist in massive quantities right in this very thin couple centimeter layer that's right at the base of the black mat. And by the way, the same diamonds, including lonsdaleite, are reported at Tunguska. So here we have an event with none of the classical markers for an impact, and yet there are diamonds there too. So you know, I think the whole shift has to be away from classical impact markers. We agree this did not hit the ground, this did not leave a big crater, but it leaves the same markers that Tunguska had, which all three of them will admit was an impact. It just hit the air instead of the earth. All three of the
speakers to the left-hand side of the table have come up with one single agreement that in the YDB, at the boundary where we find the diamonds and so on, we do not find shock quartz or classical indicators of shock characteristics. Now, I'm older than dirt, and when Gene Shoemaker and Ed Chow did the first diagnostic test on Meteor Crater to prove it was a crater, I was a graduate student at that time, and my mentor had a NASA grant, so I spent my PhD years developing shock criteria. So I'm not necessarily ignorant of the various structures that we see in shock minerals, but there are craters and craters of where you can't, there isn't quartz or there isn't something else. You don't have all the remarkable shock indicators necessarily in one event. I might add that the comparison of diamonds, nanodiamonds in the YDB and the KT, Cretaceous Tertiary boundary, has nanodiamonds also. It has shock diamonds. Not above, not below, but in the very thin layer as we see them in the YDB. So there is a nice analogy there that we have the diamonds and we don't have shock quartz. I worked with the Alvarez group in Berkeley as part of their project team for 10 years, collecting materials and looking at the various sites as they were developing their theory before, during, and after the Chicxulub. Of the 168 sites, as I recall at the time, these are from ocean cores from around the northern hemisphere. 34% of the KT boundary did not have shock indicators. It was loaded with fullerenes, loaded with soot, loaded with iridium, but did not have shock indicators. When an asteroid, an impactor, makes a crater in the Earth, you have various layers of rock that is part of the target. Some of that material, the top material, will be totally vaporized, blown away. The next huge layer down, like at the Chicxulub crater, which was gypsum, 1,500 feet of gypsum, that will vaporize. There's no quartz in gypsum. So it depends on the target material, the distribution of the ejecta as it comes out and is distributed globally. Now, I'm not saying we expect to find quartz at the YDB, because I don't think we made a crater. We may have penetrated, as Carolyn says, a big hole in the ice in Canada and may have scorched the underlying material, burning a lot of material, maybe partially making the carbon spirals, I don't know. But the fact remains that we have shock diamonds, we have diamonds, we have a lot of them, and we have melted carbon. Something happened, and we point to a shock event. We don't know the mechanism. That's what we're all working on, and I hope my colleagues on the left-hand side, the central side of the table, will help us in the future and help develop this to a more fulfilling end. We have hyperballistic experimental people on board to do, and I want to either get Mark or his colleague David Crawford to help us out here in some way. We'll work one against the other on that one. Maybe a couple other comments here. Mark said, well, statistically, this can only happen 1 every 10 million years. And we had trouble with the NEO people when our hypothesis first came out, the near-Earth orbit people that keep track of and try to find potential hazardous comets and asteroids. And my old boss at NASA, David Morrison, who's big in the NEO playing field, said to me, you can only have an event like this large, 1 every 100 million years. And the one in Chicxulub was 65 million years ago, therefore you can't have another one. You could have 3 in 100 million years and not have any for the next 200 million years. Statistically, it's the same. You can't use that argument. Then they said, oh, we keep track of everything. We know where everything is now, which is not true, because since last year, 5 new comets, new asteroids, which they didn't have a clue about, appear, say may be hazardous. So you can't use statistics to win an argument. Politicians do, but we know who they are. One other thing that Mark mentioned, about a year ago there was a strange event in Peru. A crater had formed by a small meteorite, about a meter and a half in diameter. And this, according to the physicists, say this is impossible. You can't get a meter and a half object through the atmosphere and still retain a velocity that is sufficient to create an impact. And this was a beautiful impact crater, 15 meters across, 3 or 4 meters deep. So again, it happened. The evidence was there. It was real, but it was impossible. So we're in the sort of same scenario here. What we're saying is maybe this is thing, and other people are saying no, it's impossible, but it happened.
Just add one other follow-up too about the diamonds. One clarity there is almost all the diamonds we see did not come from outer space. They were formed on this planet. In fact, we find them inside these carbon spherules. Each one of these little carbon spherules, which averages about the size of the period at the end of a sentence, has more than 1 billion diamonds in it. Now, they're very small, but they're in there. So we were curious about how they could be there inside this carbon. So we reverse engineered the process, and we actually learned how to make them. We were able to create carbon spherules. They're made of tree sap, charred tree sap, and under the right temperature and conditions, we could create diamonds in them. It turned out to be so unusual that we have a patent application on it. No one had ever heard of this way to make diamonds before, but they're under such extraordinary conditions. They're not real-world conditions. It takes about 1,000 degrees C to form them, very intense heat. It's capable of, forest fires are capable of doing that. But the real key to making these diamonds is almost completely excluding oxygen. So if you have a steam atmosphere or argon or nitrogen, then the diamonds will condense inside the carbon, but without that, they actually burn up just like the head of a match. So we know how to make the diamonds. We're pretty sure how they were made, and what it requires is what we think are the exact conditions that would happen inside or very near the fireball of an explosion, an aerial explosion. That explosion eats up a lot of the oxygen, pushes the atmosphere aside, and it's almost a vacuum inside the fireball itself. And under those conditions, the diamonds can form. We've proven that in the laboratory. We've duplicated those conditions. We can make the diamonds. So we're certain that almost all of these diamonds were formed on the planet, and they were formed 12,900 years ago. Now, maybe if someone can come up with a better explanation for an impact, that's good. But so far, most of our critics say, well, that can't work, that doesn't make sense, that's not good. But they don't come up with a mechanism. How do you get quadrillions of diamonds? Remember, there are 1 billion or more in the sediment the size of my thumbnail, and they're only under the block map. They're not in it, they're not below it, they're not above it. So my question is, if they don't like our hypothesis, what would be their suggestion on how this formed? This is extraordinary. We've looked through as much as 100,000 years of sediment from modern days back 100,000 years ago. There's nothing like this. So this is not something that's just going on commonly. Every 100 years or so, you have all this stuff forming. It's just not there. So if it's there, how did it get there? We're open to suggestions about how it got there. We don't think we've got all the answers by any means. But on the other hand, let's get past saying, well, I don't like that idea, or I don't think that happened. And let's get to the point, well, if you don't like our idea, what's yours? How did it happen? But don't dismiss it. It's so rare that it's not occurred but once in the last 100,000 years. And that's only as far as we've looked.
Okay, what I'd like to do is have a response now from the other side, as it's been characterized. And then I'd like to open it up to questions from the audience. I see that we have about 20 minutes left here, so I'd like to continue the interchange.
The information you just put out on the source of the diamonds is brand new, so we haven't really had time to fight back. vapor deposition diamonds, is this something that you're homing in on, the technology used in vapor deposition diamonds?
Well, no, it's different than that. They seem to condense in the matrix of these spherules, so it's a carbon-rich matrix. They actually grow first as graphite, then under. Yeah, what we find in this carbon matrix is amorphous carbon, it's dominantly carbon, a little bit of other things. And we find that for some reason, under the right conditions of temperature and anoxic conditions, that small domains of graphite will form inside these carbon spherules, given the continuing heat and not much pressure, it's atmospheric pressure, but it requires anoxic conditions, is for some reason, some of that graphite will go ahead and turn into diamond. And we've duplicated this under lab conditions. We can reliably produce diamonds as much as you want, under our conditions. The curious thing, as we found, is that the companies who are making activated carbon, do any of you have aquariums, or many of you take pills, these little packets in your pill bottles, activated carbon. Well, believe it or not, we found that the vast majority of that commercial activated carbon contains nanodiamonds. Almost all the manufacturers in the world are making fish tank carbon that contains nanodiamonds. They don't know it until we told them, and we're trying to get them to pick up our patent now. But the curious thing is, the key to their process of making activated carbon is you cannot let oxygen get into the process. They exclude oxygen completely. They keep your activated carbon in your fish tank. They keep it under steam conditions. In other words, they limit the oxygen, and these diamonds just condense right out of the carbon.
Remember I told you that we had proprietary information, and Alan's just let part of it out of the bag. I'm going to beg a little absence here and leave him to fight the other side. I have a hydraulic problem, and I'll be right back.
I think he says he really needs more coffee, not getting rid of it. Okay, well, this throws a new light on, and that's what scientific debate is all about. During last night's presentation, I got the impression that the diamonds were from the projectile itself. And here we're throwing out a different card, and no, you're accounting for one of your markers by incinerating in the absence of oxygen. In other words, you've got a giant charcoal kiln that's going full bore. That doesn't really offend me very much. We do see evidence for that kind of mechanism at the Cretaceous Tertiary boundary, and that is 65 million years old, not a little piddly 10,000 years in a geologist's eyes. So you would expect more fragile data to be able to survive. I'm a little curious about why do you call a radioactive bone layer an ET marker? Where does the radiation come from? Why do you call a radioactive bone layer an ET marker? Where does the radiation come from? What is the source?
Yeah, actually that shows up in sediment from the KT2, and it has nothing to do, I think, with the impactor. It has to do with redox conditions that happen afterwards. So if you have an environment that will dissolve out iron and radioactivity, then it gets mobilized in the environment. But if you look at some of the ocean cores from the KT, you'll see that uranium and thorium and potassium-40 do tend to peak there too, along with lots of other things. And it's just part of that chaotic environment, but it's impact related, but only secondarily. So you can have peaks for other reasons too, not just that. So.
Comments?
Last night at the presentation, and believe me, that was a beautiful presentation. I was in awe of your PowerPoint. I don't agree with it all, but it was beautiful. And I wish that I had more time.
Like the art, but not the science.
I wish that I had more time to absorb all of it, because you went very quickly, and this is indeed an involved situation where you have so many markers and so many ideas being thrown out all at once. All of these ideas, therefore, in my mind, require lots of substantiation. You need a lot more work on all of them, I think, before we can truly accept the idea that this was an impact. Now, one of the ideas you presented last night was that this was caused by a comet breaking up, and these fragments of the comet then created this situation throughout two hemispheres. Am I correct? All right, that is indeed a big comet to have fragments that would be big enough to come through the atmosphere and break up without coming all the way down. I guess I like to envision these things, and I can't quite see this happening, nor do I see it happening simultaneously to cause what you say was an event that happened instantaneously. To me, that means it was one moment and then the next moment. And I tend to think in terms of geologic time or astronomical time, where they talk about things happening very quickly, but that means many, many years. This sort of impact would have to happen pretty quickly as an airburst. And if it happened as an airburst, I know one of the effects would be as shock wave. You would have an airburst, a luminous wave, which would cause effects on the ground. But could that sort of thing, those pressures, cause the markers that you're talking about? I don't know. But that one really does concern me. There are not many comets that we do not have some record of in this particular period of time. If not us, the Chinese, who have records going very far back. But the comet idea still worries me. Now, the other possibility, of course, is that it was a meteor, an asteroid, and those are more likely to penetrate than comets. But an airburst is certainly an intriguing idea. I won't dismiss it out of hand, but I don't understand all of the effects yet, and I don't know how to help you on that.
We don't either, Carol.
Okay, I wish I'd have kept a piece of paper here because I've been thinking of all the things I want to say and I could go on forever. So I'll try to hit the high points. First of all, you referred to us as cynics, and we're skeptics, not cynics. If we were cynics, we'd be very suspicious of your motives and we'd have bad attitudes and maybe, and I've known Carolyn and John for a long time, and they're not suspicious, negative people. We're skeptics in the sense that I described with Carl Sagan. Extraordinary claims require extraordinary evidence. That's the skepticism that we're using to approach this. Now, you mentioned the whole statistics probability argument, and you quoted David Morrison, who's one of the near-Earth object people, as saying that, well, we already had one event in the last 100 million years. We can't have had another one. And I know David Morrison, and I know he understands that the events are independent, and you can have a second one. And that's not the argument. The argument really is, and somebody compared it to going to Las Vegas. I guess that was, I'm sorry. Alan. I'm sorry. So the probability of getting 4 aces is very low. And so the analogy to me is you've got somebody's dealt you a hand, they're face down, you pull up an ace of spades, and you're claiming you have 4 aces based on 1 ace of spades. And I say, I need more evidence. I don't think that's sufficient evidence. I know the probability is very low that you have 4 aces. And now you're saying, well, if I don't have 4 aces, what do I have? I don't know what you have. I could say, well, you have a royal flush, you know, all spades. And I think my hypothesis is just as good as yours. But I'm not going to say that because I don't know what you have. I don't know what the cause is. I do know that abrupt climate change is common, and nobody knows what causes them. We have evidence for these happening just as fast at other times in Earth history that don't appear to have any association with an impact. Now, we talk about possibly a 4 or 5 kilometer diameter object that broke up into maybe 1,000 pieces. Well, even if it broke up into 1,000 pieces, each one of those is 400, 500 meters in diameter, and objects of that size are not airbursts, do not create airbursts like Tunguska. Tunguska was probably 40 or 50 meters in diameter. In terms of mass, you know, mass scales is the cube, that's the 1/10%, the mass. So these things are going to go punch right through the atmosphere as if the atmosphere is not there. They're going to hit the ground or the ice sheet, and they're going to create a crater that could be 5, 6 miles in diameter. Each one of those 1,000 impacts is going to do that. And I'd be really surprised if every single one of those hit the ice sheet. There's going to be a big crater somewhere. There's probably going to be a lot of big craters. So that aspect doesn't make sense to me as well. I don't see this as being an airburst. And then going back to the probability issue, you know, the unlikelihood of something that big, that recent, it's even more, you're invoking or you're coming up with an explanation that's even more rare than that. In fact, Shoemaker in his 1983 paper suggested that only something like 10% of impacts are from comets, and I think that's, you probably know, Carolyn, it's probably even less than that now. I think people are saying now it's more like 1 or 2%. So now if it's an object that only, a size that only impacts once every 10 million years or so, if a comet of that size only hits every billion years or so, and now to invoke a comet that's actually broken, and it can't have been broken for very long, because if it's spreading, you know, at a rate that's greater than the escape velocity, well then maybe only one piece is going to hit. The size of the broken comet, the cluster, is actually bigger than the size of the Earth. And if it's not spreading by a rate greater than the escape velocity, well then it recoalesces and it becomes a single object again. So now it's even a more extreme improbable event. So my main argument is against this is it's so improbable that something like this could have happened. It seems almost like a magic bullet hypothesis. So I'll stop there.
I would like to open it up to questions from the audience at this point.
Can I say just back before we went to Apollo, Harold Urey, a Nobel Prize laureate, was looking over at that time the 2 main origins of the moon, and both were proven to be impossible, and Harold says the moon does not exist. So I think that's where we are.
Okay. Yes.
So one comment and a question. Back in the 70s, early 80s, I'm not sure which, Phoenix experienced about 2 or 3 100-year floods in about 5 years, as far as probabilities. My other question is, can the panel explain why they think all that ice melt occurred at the YD to change the circulation? What's the probability of a comet causing that ice melt?
Okay. The question is, what caused the ice melt that has been proposed to have shut down the Atlantic conveyor and changed the climate, at least in the northern hemisphere? What would have caused the ice to melt?
Well, the ice was going through deglaciation anyway. We're not sure that's an exact connection, but it's well known that any kind of impact into the ground creates a lot of thermal energy. If it hit the ice, the same thing would have happened. Now, the curious thing about there were what they call Heinrich events. They're purges where they're huge breakups of the edge of the ice sheet, and the North Atlantic became flooded with icebergs. Well, that happened on the average every 2,000 years, but it also happened at 12.9. But the difference was that that event was unlike all of the others. There was a predictable pattern that they saw for the breakup of the ice sheet, and the one at the time of the impact was not common. It was very, very different, leading some of the researchers to hypothesize that it didn't fit the pattern. In fact, they didn't even include it as one of those melting events for a long time, and so they had to go back. They had called them Heinrich 1, 2, 3, 10, and they had excluded this event. They finally went back and called it Heinrich 0 because they hadn't started numbering it as 1. But it was so unusual. But what happened is, what we think is that the explosions over the ice sheet are capable of generating seismic events. When Tunguska blew up, they detected it on seismometers in many places around the planet, so it looked like an earthquake. So it's capable of sending shock through the atmosphere to the ground. The ice sheet was already unstable, breaking off at the edges, so the idea is that, and this is well known, not by us, third-party research has shown that 12,900 years ago, the entire coastal edges of the ice sheet began to calve and break off. And not only that, the ice dams failed at all these string of big lakes like Agassiz, Lake Hind, if you were there last night, a whole series of these glacial lakes. There was a cascading meltwater flow that was suddenly and inexplicably blocked going south through the Mississippi, and instead it routed out north and east off the ice sheet. And when that happened, the entire North Atlantic became filled with icebergs, which cooled it just like they cool a drink of water, and it became capped with meltwater, and that shut down the conveyor, which triggered the climate change. Now, as Mark rightfully pointed out, there are any number of climate changes, and you don't have to say, well, every climate change required an impact. There are lots of reasons climate changes happen, and most of them are related to the conveyor. When that conveyor shuts down, it's like the plumbing system, the hot water plumbing system for your house. If you shut off the heat in your house, it gets cold. Well, the same thing happens to the ocean. Without that conveyor, no water into the North Atlantic. The North Atlantic became very cold, and so did the eastern seaboard, Greenland, and Europe. And you can see it in all the records. Now, we don't know that there's an exact connection. That might well be coincidental. But the fact that it happened exactly at the time, and in Lake Hind in particular, where we've gone down and sampled the cores, right at the level where the ice dam failed, and we know that because of the change in the flora and fauna in the lake. We know that the lake catastrophically drained right at the time of the event. We find iridium, diamonds, carbon spherules, magnetic spherules in this very, very thin layer exactly where the dam failed and exactly where the Younger Dryas began. Now, maybe that's a coincidence. There are odd coincidences in geology and nature. We don't dispute that. But we're suggesting that there's likely a connection.
You mentioned the Tunguska River in 1908 in Siberia. There was a comet-like explosion, an airburst, which destroyed 400 miles of timber, and I think we're all in agreement on that. What you guys are positing is kind of the same thing, but you're saying that it broke up. So my first question is, how do you know it wasn't like a Tunguska, or maybe there was a thing that broke up? That's the first question. Then the other question is, Mrs. Levy suggested that if it did hit, there was an impact on the ice sheet, that it would have left a crater. Wasn't the ice sheet at that time 1 to 2 miles in thickness, and could you talk about that?
It was 3 kilometers, 2 miles.
Let's take that last question first. I think the question has to do with how thick was the ice and what the effect would have been of an impactor hitting an ice sheet of that thickness.
Would it make a crater?
Would it make a crater? Would the ice be able to absorb the energy and not leave a crater? I think that's the question.
Yeah, and it's a complicated question, but for those of you that were last night, you saw the Ames vertical gun experiments with Pete Schultz. Well, Pete looked at this very question. what happens when you take an impactor and you hit it into a block of ice? What does it do to it? What does it do to the substrate beneath the ice? And curiously enough, he found that it's angle dependent. Now, Mark mentioned that these large 300-meter objects would make it through the atmosphere, but that's not true. Under certain conditions, they don't, and it's angle dependent. Now, it's just as likely that an object come in at 15 degrees, 30 degrees, 45, or 90. Every one of those is equally probable. It can come in, particularly if it's a comet. Comets are known to come in from any direction, so it could have hit Earth from any direction. What Pete found is that at 30 degrees or less on his angle, if he took what the equivalent was a 2-kilometer object, and he blasted that at cometary speeds into a 2-kilometer thick ice sheet, it would have blown a 2-kilometer hole and absolutely untouched.
We've run out of gas.
We can take offline questions. We'll be around for a while.
Can you hear me?
Okay, I think Mark may have a comment on the low angle impact.
Alan needs to finish. Alan needs to finish.
Did that answer your question?
Yeah.
Which 4 of your questions didn't that answer?
Didn't hear you at less than or equal to 30 degrees.
That's what he found. Yeah, less than equal to 30 degrees, or a 2-kilometer object, and we don't think it was that big. Although Shoemaker-Levy, Carolyn's own comet, the largest piece, was thought to be only a kilometer, the largest piece. So at 30 degrees, if Shoemaker-Levy had hit this planet, it would have not poked a hole through the ice sheet at 30 degrees or less. If you get 90, then it's a different story. And this is well known. This is not our information. It comes from Jay Meloche at University of Arizona. There are a lot of calculations about what it takes to create a certain size crater. And this is right from their calculations. That angle and that size is just all.
Okay, I'll respond. Alan said some things that are correct and some things that are incorrect.
Opinion.
Let's start with the incorrect things. One is that not all impact angles happen with the same probability. The most probable impact angle is 45 degrees. As you go to the vertical, it becomes less probable. As you go to the real grazing impact, it becomes less probable. So now we have a probability argument again. So now I have to add another, factor of 10 or something. If it, it's already improbably large, it's improbably broken, it's improbably a comet, and now it's coming in at an improbably. it's more like 5 aces. But the part about low angle impacts being less likely to actually hit the ground and make a crater, that's true. And the part about the largest fragment of Shoemaker-Levy 9, that's still debatable. My co-author Dave Crawford estimated that the largest fragments were about 1 kilometer. But a 1 kilometer object coming into Earth's atmosphere at 30 degrees will definitely hit the ground and make a crater. If it comes in, at an extremely low grazing angle of a few degrees, then it goes through so much atmosphere that it burns up and only the last bits hit the ground. You'll still have a major effect on, a major effect on the ground. So again, I think we've gotten to an extremely improbable situation.
One more question. Yes.
Yeah, your panel of contras is great, but no offense, they're all physical scientists. What we haven't heard this morning is contradiction or support from the biological and ecological side, and I can think of mega questions and micro questions there. Why are the terrestrial megafauna selectively wiped out? And the other is on the micro scale, ultimately, what species or genera of algae are involved in these mats? What is their geographic distribution? Is it all the way from Catalina to Europe? What's going on there?
Okay, the first part on the size is that one problem with the geologic record, paleontological record, is that small bones just don't survive like big bones. So it's skewed towards the bigger animals in the first place. It's almost impossible to find bird bones, even though birds were far more common than mammoths. There are probably a lot more mammoths found than there are small birds. So part of it is a matter of it just didn't exist, it didn't survive the record. But the other thing is that we think that the fire was the biggest problem with this event, that we have massive evidence of fire at every land-based site that we looked at. So if this thing set fire to grass and trees, then most of the animals wouldn't have had much to eat. We doubt whether the impact itself killed most of the animals. We think probably starvation did. And Vance Haynes has an interesting idea. He finds evidence for freezing of the lakes in the San Pedro Valley in southern Arizona, and his hypothesis is that without water, most of these animals could have survived only a few days. Without food, they could have gone longer, but water would have been crucial. And so whether that's true or not, I don't know, but at any rate, it seems to be the grazers were the ones that were most in danger. They needed the most food, the most water, and those might have been in short supply. The generalists, including people who were pretty much omnivores, were in the best shape. They could eat anything, including all the dead megafauna, at least for a while. So it's a little harder to say, but the grazers were the ones that really went out, and then the animals that fed on the grazers were in trouble too.
Ladies and gentlemen, I'm afraid we've run out of time. I want to thank everyone for coming. I especially want to thank our panel for coming today. I hope what you've heard today gives you a sense of what this debate is about. The stakes are very, very high. The issues are very, very important. I hope you continue to follow this developing scientific debate as it goes on, because it's of extreme interest and importance to North American archaeology. Thanks again, everybody.